think of snow depends a lot on where it falls. If you live in eastern US, it may be fun. Or maybe it is just a pain. But if you live in those parts of the world where they depend on snow,
for a large fraction of their water, they use it for drinking, for agriculture, for industry, for electricity. For snow is a very important natural resource. In western parts of USA, 80 to 90% of their renewable water comes from snow.
Snow cover is just one part of the cryosphere that many of us have actually encountered before, but it also plays a critical role in regulating Earth's climate.
Through decades of remote sensing, we now have a 52-year record of snow cover in the Northern Hemisphere. And we can see changes in the amount of snow cover over in the time period of particularly last few decades, where we can say that snow cover is melting a lot earlier during springtime.
But analyzing snow cover isn't that easy. What is tricky is though how much thick is that snow, and it's even trickier how much water is in that snow.
That tricky part is known as snow water equivalent, or how much water would be there if snow melts.
NASA and its partners have taken to air to help solve this elusive mystery. First, there is Airborne Snow Observatory, a small plane equipped with a couple of instruments, one of which measures snow depth using LiDAR. LiDAR measures distances using lasers. Since 2014, the plane has flown over basin in California and Colorado. Taking before and after look at snow depth, scientists have collected snow-free summer data and snow-on-winter data to get an idea of snow depth.
Still, there is no single way to measure snow depth across the globe. Therefore, NASA's other campaign, SNOWX, is testing other combination of sensors. This winter, SNOWX will test a new instrument: snow water equivalent synthetic aperture radar and radiometer, or SWESR.
SWESR has two main components, one of them being radar and second one being radiometer.
Radar provides depth of the snow, and radiometer provides density of the snow. You can put those two things together to get snow water equivalent. In this chamber, we are going to study these radiations that are at different frequencies. For systems are running in the chamber to enable us to isolate types of radiations and interferences. In about a month, we are going to take the instrument, mounted on a plane in Grand Basin of Colorado, to take various measures. This is what we call it an engineering flight.
Making sure that sensors are calibrated is key in order to face natural challenges. Half of the area that is covered by snow contains trees and forests, which makes it difficult to measure actual snow depth.
After the snow gets a chance to settle on the ground for a while, it becomes denser with the time and changes. That is another reason why snow measurement is a great challenge. It doesn't stay the same, it is changing constantly. One of the things we do in the field is digging the snow. We call snow pit. We dig literally snow pits to see the different layers of snow, which are very important.
All this digging is part of ground SNOWX, a way to match up with airborne instruments, to see what is actually sitting on the surface. The ultimate goal of SNOWX is to figure out what the best instruments would be for the future satellite missions, to get the global picture of snow.
We need to know how much snow is in the snowpack. If we have too much snow and it melts too much fast, there would be flooding. If we have less snow and it melts very early, there can be long wildfire seasons, deadly droughts.
These facts must be accounted for if we are to manage our water resources efficiently. On the next episode of Cryosphere, we shall discuss the intricacies of sea ice,